Hello, everyone. Today we're going to be learning about the conservation of angular momentum. So first, before we get into the main concept, we're first going to go over what is angular momentum. Well, angular momentum is very similar to linear momentum, and we can think of linear momentum as when a ball, let's say the ball has a mass of m, and the ball is moving with a velocity of the ball is moving with a velocity of v. And so the of this, which we're going to write down, would be equals mv. And so basically, it's basically a linear momentum describes the strength of an object's motion. And now when we're talking about angular velocity, it's very similar in the way, except instead of defining the length of an object's linear motion, you're defining the length of an object's angular motion. So let's take the same ball, has a massive, has a moment of inertia of m. So instead of having a mass, which represents the resistance to change of a force, we're doing the object's resistance to rotational motion. And let's say the object is moving at omega velocity, angle, like radians per second. And so now the equation for angular momentum be L, which is the normally use L for to define angular momentum, is equal to L equals to moment of inertia, or I, times angular velocity, or omega, lowercase omega. And so now, similarly to linear momentum, where you have the conservation of linear momentum, you're able to say, define the initial momentum of a closed system never changes. You're also able to define that the angular momentum in a closed system does not change. So it will be L, let me just fix that. Li equals Lf. And the units for angular momentum, by the way, are kg meters squared per second. So then let's move on to a basic example of angular momentum. And often, it's seen very often through, this is a very common example many people use. Oh, let me just fix the ballet dancer. But basically, it's of a ballet dancer twirling, and I know it's not the best drawing, but I try my best. And since the ballet dancer has her arms out, she has a higher moment of inertia. So yeah, she's, just to make sure you understand it, she's twirling, and let's put that there. And she has a moment of inertia of 4 kilograms meters squared. And she's currently moving at 2 radians per second. And so we can calculate angular momentum by multiplying them together. So her initial angular momentum is 4 times 2, and you get 8 kg meters squared per second. So now let's say the ballet dancer then pulls her arms in and like basically is like doing a hugging motion of herself. And this causes her moment of inertia to change to 2 kilogram meters squared. And so now so now the question may ask you, what is her final angular velocity? And to do this, you can then use the conservation of angular momentum. So you know that Li is equal to Lf. And we already solved for Li, so we could just plug that in right there. And you get 8 is equal to her I omega final. And we define that her I value is 2, so we're just going to substitute that in. Equals 8. And that means her final angular velocity will be 4 kg, sorry, not kg, I mean radians per second. And so now using angular velocity, we were able to predict that conservation of angular momentum, we were able to predict the new speed of the ballerina dancer. And this has many other uses. Let's move on to a more advanced example of angular momentum. So let's say you have two disks. The first disk is rotating with the first disk has which we'll name disk 1 is on the bottom, and it's rotating at 4 radians per second with a moment of inertia of 3 kilogram meters squared. And next you have another disk 2, which is stationary. So it's moving at 0 radians per second, and its moment of inertia is 2 kilogram meters squared. And let's say you drop disk 2 onto disk 1 in a way that their centers align. So that means their moment of inertia is all you have to do to find the total moment of inertia of the system is to add them up. And so what is the new angular velocity of this combined system? Well, like in the previous case, you want to calculate Li equals LF. And to do that, we need the angular momentum for both objects. So for disk 1, we're going to label it as I1 initial. Actually, we'll just label it I1 times omega 1 initial. No, we'll just say omega 1 plus I2 omega 2, and then we can then say, because the objects are sticking together, we can kind of think of this as an inelastic collision. So in this case, we can combine the moment of inertias for both objects. And then you trying to solve for the omega final. And so then you can plug in all the values. Remember, because the second object, the angular velocity is 0, that means that it has 0 angular momentum. And then let's just plug in all the values. So it would be 2 times 4 is equal to, then you add the moment of inertia, so that's 2 plus 3, and then and so this will just be 6. Oh, sorry, made a small mistake. It's not 2, because remember there's moment of inertia of object 1, so it's actually 3. And then this 3 times 4 is 12, and you divide by 6 on both sides, you get an angular velocity of 2 radians per second. And so as you see, the angular velocity of object 1 was able to decrease, while the angular velocity of object 2 increased. And basically they're transferring some of the momentum into this combined system, and the reason why the angular velocity of object 1 decreased was because its moment of inertia increased, which would make it harder for this combined system to turn than the initial object. So let's move on to the next example. Now here I have a diagram of an orbit. And this is an elliptical orbit. We can say like this is the sun, and this is a random planet that's just orbiting the sun. And so now you may be thinking, well, how does angular momentum conservation of angular momentum be able to be used here? Well, let's think about it for a second. This object is moving in an orbit, which is, while not circular, in a circular type of shape, like an ellipse. It's moving in an elliptical shape, which does have curved turns. So this is we can use angular momentum to calculate the speed of an object at its perihelion and aphelion. Aphelion and perihelion. Sorry, this is aphelion, perihelion. And then we can do this But for this equation, we'd have to change the we would have to make some assumptions about the planets. So we know that angular momentum is I omega, correct? And now let's assume that the planet is a point mass. So that would make the moment of inertia of the object mr squared. And then we know that another way of writing angular velocity is we can write it in terms of velocity. And we can write angular velocity as v over r. And so now what our final result is, we get m v r. However, there's one big difference that we have to make. And you have to remember that the velocity vector, so let's say you have it at the aphelion here, the velocity vector of the object is moving this way. So it's moving perpendicular. So they're not moving in the same direction as the radial distance. So like the radial distance, it's from the foci, which we'll call the sun, to the planet, right? And we're gonna have to change the velocity so that they move in the correct direction, because we have to do some vector multiplication. And so for that reason, we have to find the perpendicular of the two versions. And that generally entails multiplying it by the sine value of the angle between the radial distance and the direction velocity is moving. And since in this scenario we're talking about the aphelion region, we can see that the angle between the velocity and radius is 90 degrees. So then we can just transfer that to the equation, and we multiply it by sine 90, and sine 90 is just 1. So in the end, in this scenario, if you're trying to find the angular momentum of the object at the aphelion, it would just be mvr perpendicular, where m is the mass of the planet, v is the speed that it's moving at currently, and r is the radial distance from the foci point, which we're using the sun in this case, to the planet. And this is actually how Kepler's law, Kepler's law was invented. And they use angular momentum to create the equations for Kepler's laws, for some of Kepler's laws at least. So let's move on to a more complex example that uses the new way of representing angular momentum. So let's say we have a ball that's traveling towards a hinged at this point, right? Is hinged at that point right there. So that means that this door will rotate around that point. And the ball is moving in a straight line towards the door. So how are we able to model the angular rotation of this object? You might be confused for a second here. How can this door be able to rotate how can this door be able to gain angular momentum when this ball, which should have like all the momentum in the system right now, because since the door is stationary, right? Since the ball has all the momentum and it looks like it's traveling in a straight line, how does the door gain angular momentum after it gets hit by the ball? The answer is really surprising. And it may be intuitive to think that this ball has no angular momentum, seeing that it's not really curving around an object or not really rotating at all, because let's just say the ball is traveling straight without rotating at all. This ball still has angular momentum, but it has angular momentum. You just have to consider the perspective from where you're checking the angular momentum. And if you were observing the ball's angular momentum from the rotation point, which again is at the hinge, you can see that the ball actually does have angular momentum. And it's actually modeled in the same way how a planet, the angular momentum of the ball it's modeled in the same way a planet is the angular momentum of a planet is while rotating around the sun. And so we can then say that the angular momentum of this ball, is equal to mvr perpendicular, where m is the mass of the ball, v is the velocity that the ball is traveling at, and r is the distance from the rotation point and the ball. And times, and remember, because we're multiplying vectors together, we have to make sure that, since this is we're not doing a dot product but a cross product here, we have to make sure it's perpendicular to each other. And in that case, we'd use sine and then the angle that is created between the velocity and the radial distance. And so in this case, it would be mvr sine theta. And this is and an interesting way to remember this is, well, what is sine theta anyways? Well, sine theta is representing the opposite over the hypotenuse of this triangle that we created, right? And so because the ball is going in a straight line, we're assuming, the angle between the door and the ball is a 90-degree angle. So that means that the ratio will be the same. So then we'll know that the ratio that this sine thing, that the sine function represents, would be d over r, since d is the opposite and opposite side to the angle, and r is the hypotenuse. So we can replace sine theta as d over r in this scenario. And just to clarify, d is the distance from the pivot point to the point of impact of the ball and the door. And as a result, the angular momentum of this ball can be represented as mvd. And as you can see, that means that no matter where the ball is, let's say the ball is over here and it's moving at the same speed, it has the same mass, etc. The only difference is the angle and the radial distance. This ball will have the same angular momentum as the ball here, and it's also the same for a ball that's here. This ball will also have the same angular momentum as here. So the ball will have the same angular momentum, will not gain or lose anything, because remember, angular momentum is always conserved. And it will maintain the same angular momentum until it hits the door, where it will transfer some of the momentum. So let's do an example. So let's say we have a 3-meter long door that is pivoting around this point, and the door weighs 2 kilograms, and a ball is traveling at it at 4 meters per second, and it weighs 1 kilogram. And let's say the ball is going to hit the edge of the door. So now let's try to figure out the angular momentum. So remember, the initial angular momentum, we always start off with initial angular momentum is equal to final angular momentum. Li equals Lf. And we start off with the two objects in the system, which are the ball. Let's start off with the ball. So the ball will have a moment of, the ball, as we explained last time, will have its angular momentum will be represented by mvd. Since remember, the ball is going straight, and so it creates a 90-degree angle. So this would work. Plus we have to find the inertia of the door. We'll say ID times its initial angular momentum. Times its initial angular velocity. And that's equal to, let's say the ball hits the door, the ball stops moving. So what we're left is mvd plus, we're going to say this is initial and this is final velocity, plus id omega final. And we're going to solve for the final angular velocity. So for here, immediately off the bat, we can simplify some of the terms. Here, we know that the door is stationary, so it has no angular velocity, so we can say that's 0. And then we said that after the ball hits the door, it stops moving. So that means it has a velocity of 0, so we can immediately cancel out those terms. And then we're gonna then calculate the angular momentum of the ball, which we had said it has a mass of 1 times the velocity 4 meters per second times 3 meters from the pivot point, because that's where it's gonna hit it. And then we're gonna do the moment of inertia times the final angular velocity of the door. And now what would be the moment of inertia? Well, see, it's not explicitly given here. And that's because I'm expecting to calculate it here. So remember, the moment of inertia at the end of a rod is 1/3 ml squared. And L represents the distance from the door. So we can just plug that in. 1/3 ml, sorry. That L means angular momentum. So let's just say a curly L like that, squared times angular velocity. And let's just quickly simplify that. So that's 1/3 times 2 times the distance squared, that's 3 squared, times omega final, and we know this is now 12 because 3 times 4 is 12. And then we can simplify this. This is 1, and if you multiply them together, you get 6. So that means the moment of inertia of this of the door is 6 kg meters squared. And then if you divide by 6 on both sides, you end up getting a final answer of 2 radians per second. And so as you can see, conservation of angular momentum is a very powerful tool that lets us be able to calculate the final angular velocities or even the inertias of objects that are changing over time in a closed system. And this closed system has no external torque supplied. And the conservation of the angular momentum has many more applications, including how it helps explain how bikes are able to stand up while biking, and how planets orbit each other and complex systems. And that's why angular momentum is a very important concept to learn. I hope you learned something today and have a great rest of the day.